deviation limit of random walks in random environments. Hindy, thank you so much for accepting the invitation, and the floor is yours. You can start whenever you want.
Okay, thank you so much, and thank you for inviting me. This is a great seminar, and hopefully, I can't see everyone in the audience, but hopefully I'll get to meet some of you at future events. So everything I'm talking about today is joint work with Shayon Das. He is a postdoc at the University of Chicago, and with Shalin Parekh, a postdoc at the University of Maryland. Okay, so the physical motivation for what I'll be talking about is diffusions in time-dependent random environments. So first we could think of the classical setup of diffusion going back to what Brown was studying and what Einstein was studying, which is basically pollen grains that are moving around in water. This is a very classical setup. You have the grains of pollen, they're being bombarded somehow by water molecules, which cause them to move like Brownian motions. But if we want to go beyond the classical setup where we treat all the grains of pollen as independent Brownian motions, we want to take into account the fact that all these grains are moving in a shared random environment, right? So the environment that's causing them to move is the water, and then you could imagine that maybe there are some local effects in the water, like turbulence or some flow, and if you have different particles that are really close to each other, there are going to be some forces that cause them to move similarly. So in fact, the motion should not really be completely independent. And the types of physical models that we'll be considering, or mathematical models, are going to have a time-dependent random environment. So the environment is something that also changes in time. So in the talk, we're going to focus on a certain discrete family of models called the random walk and random environment. Towards the end, we might mention briefly a continuous family of examples called sticky Brownian motions. And the idea is that all of these types of models should share some similar behavior coming from the underlying random environment. In particular, we want to think about questions such as what role does the environment play on the position of the particles at time t? And in particular, how does the environment affect the outlying particles? So the ones that are moving farthest away from the bulk, maybe the largest particle or the largest two particles. And the main message that we're going to see throughout the talk is that the random environment doesn't play such a role when you look at the typical particles. So typical particles will behave similarly to just independent random walkers. But once we start looking at the maximal particles and the ones that are somehow the extremal behavior of the system, these particles will be heavily affected by this adding in this underlying random environment. And we're going to try to understand this effect. So the outline of the talk is first we're going to introduce the model, which is the random walk and random environment. Then we're going to show how in a certain regime, which we're going to call the moderate deviation regime, the quench density of this model will exhibit KPZ fluctuations. So we're going to explain what this means. And then we'll talk about some proof ideas and hopefully have time for some applications. Okay, so what is the setup that we're working with? So we're working with a time-dependent environment. So what this means is we choose some distribution omega that takes values on 0, 1. And then for every space-time point, so for every positive time t, integer time, and every integer position x, on the integers, we assign an IID copy of this random variable omega. So we have this family omega that represents our environment. And then when we run walkers in the environment, the walkers move as follows. So if the walker is at position x at time t, then it will move to x plus 1 with probability omega tx, and move to x minus 1 with probability 1 minus omega tx. This makes sense because remember the omegas are just between 0 and 1. So these probabilities, p omega, these are quenched probabilities because they depend on the environment. So these probabilities are themselves random, right? Because omega is itself a random variable. I just want to point out the distinction between a different model that's also called the random walk and random environment, which is very commonly studied, and that's the case where the environment is time homogeneous, so the environment actually doesn't depend on time, and that's a different model which behaves quite differently than the one we'll be considering. So here at every time, the environment's completely refreshed and is independent of previous times. And here are just some pictures. If there are any questions, I guess interrupt or put in the chat about the definitions. Okay, so in our model, we have some, we could play around with the distribution of omega, and that will give us different versions. This is actually a family of models depending on the distribution we choose. So we're always going to assume that our omega has mean 1/2, so that our random walks are on average centered And the variance will be sigma squared, which, because it's a random variable that takes values between 0 and 1, the variance is necessarily between 0 and 1/4. If we choose the omegas to always just be identically 1/2, then we don't really have a random environment. We're just back in the case of independent, simple symmetric random walkers, and sigma squared is just 0. So we don't have this extra layer of randomness. And the other extreme, if we choose the omegas to be Bernoulli random variables, then the omegas always take values 0 or 1. So this is the case of coalescing random walks, because if you're at some position at some time, if omega is 0, you're forced to move to the left. If omega is 1, you're forced to move to the right. So if two random walkers are at the same place, they're just going to be forced to do the same thing, and that will cause them to coalesce. That's the other extreme, where sigma squared is equal to 1/4. This is somehow, our theorems won't really cover this case because a lot of things will blow up in this limit. And then the third example I wanted to point out is if you take the omegas to be beta distributed random variables, so in particular, you could take them to be uniformly distributed on 0, 1. This is called the beta random walk in random environment. And this model was first introduced by Parekh and Corwin. And we're not going to talk so much about this model, but what's interesting about it is that for this model, there's you're able to write out certain probabilities using exact formulas in terms of contour integrals. So for this particular model, you have very exact formulas, and you could take precise asymptotics. So some of the conjectures that we'll mention have only been proven for this case, because this was one of the more amenable cases to study. Okay, and then just it'll be important to just keep in mind that this probability P superscript omega is a quench probability. So it's itself a random variable because it depends on the randomness of omega. We also have, we could also take, I don't know what we call it, the blackboard font probability and expectation with do you see when I highlight something? Okay, with respect to the law of omega itself. So if we average out the quench probability with respect to the law of omega, that gives us another measure, which we call the annealed law. So the main thing that we want to study in this talk are these quenched transition probabilities, or this quenched density. What's the probability that the random walk will be at position t at time x? We just denote this shorthand by p omega t comma x. But sometimes we'll also need to consider the annealed motion. So if we look at k walkers, but we average out the environment, we'll call that the k-point motion. The 1-point motion, for example, is just going to be a simple symmetric random walk, because if you have one walker and you average out the effect of the environment, you just get a regular simple symmetric random walk. The k-point motion will be a bit more complicated because you'll have to average out but still take into account the interaction. So in particular, that if we have two walkers, we're going to end up having some type of sticky interaction. So if you imagine that two walkers end up at the same place at the same time, they are going to tend to stick to each other. And we can make this more precise by trying to understand, suppose we have two walkers that are at position x at time t. What's the probability that they're going to stay together for time t plus 1? And there's two cases. Either they both jump to the right, which will happen with probability omega tx squared, or they'll both jump to the left, which happens with probability 1 minus omega tx squared. So we see that the probability that they'll stay together is this sum, but this is still a random variable, right? Because we're still working with the quenched probability, which is random. We could take the expected value of this random variable, and we see that it's equal to 1/2 plus 2 sigma squared. So in particular, it's always at least 1/2. So in the worst case, it's just a 50-50 chance that they'll stick together. But then as we tune the variance of the environment to be larger, they're going to tend to stick more and more. So when two random walkers touch, there's some sticky interaction. And I said I'll maybe mention at the end if I have time, but there's a way to kind of take a diffusive scaling limit of this RWRE model so that the random walks converge to Brownian motions, and in such a way that you still preserve the sticky interaction. So if I have time to talk about the other model, you could kind of think that it comes from just taking a continuous limit of this type of interaction. Okay. And like I said, what we want to study are these quench densities, and because they're random, it makes sense to ask about their fluctuations. So the type of result that we're going to be talking about is, what are the fluctuations of this object? Before we get to stating the result, I need to introduce the KPZ equation, because that's going to be the random object that dictates the fluctuations that we'll be studying. So the KPZ equation is a stochastic partial differential equation that was introduced by Kardar, Parisi, and Zhang in 1986. And the solution is denoted by HTX, where T is time and X is the spatial parameter. And then it's an SPDE, where basically the first two terms are just the heat equation, right? So the time derivative of H is equal to the Laplacian of H. And then we add in this nonlinear term because it's the square of a partial derivative of H. And then the last term, we have some noise coefficient, so just some positive real number. And that tunes the randomness. And then we have C, which is a space-time white noise. So this is what makes this a stochastic PDE, because we're adding in this random term. And this equation is quite difficult to, make sense of. And there's a lot of work devoted to making sense of solutions to this equation. But for the purpose of this talk, we're going to use a particular notion of solution, which so we won't have to worry so much about working with the KPZ equation, because we're going to somehow define the solution to the KPZ equation to be the logarithm of the solution to maybe a simpler equation called the multiplicative stochastic heat equation. And in fact, this could be justified rigorously if C were something smooth or a nice object, then it would be quite simple to show that if you took, the log of a heat equation, you would get this equation. And somehow it turns out that you can make this precise even in the case where C is a white noise. So we're going to basically work with this multiplicative stochastic heat equation here, which is basically a heat equation, but we add a term. Again, we have gamma, which is the coefficient, and then we have the solution U times a white noise. And then we're going to somehow say that the KPZ equation is the logarithm of the stochastic heat equation. And we're always going to work with Dirac delta initial conditions for the stochastic heat equation. And it turns out, since we somehow remove the nonlinearity, there's a well-defined solution theory for the stochastic heat equation. So these are the objects that we'll be working with. Okay, so now for the situation that we're actually interested in, we want to study this quench density P omega, and there are different regimes in which we can look at it, right? So since these are diffusions, we know that typically at time t, a particle should be at a position that's of order square root of t. So if we look in this diffusive regime where x is of order square root of t, this is the typical behavior. And like I said in the beginning, we really expect that the typical behavior is somehow similar to the setup of independent random walks or independent diffusions. In this regime, we expect to have basically Gaussian fluctuations. On the other extreme, we could look at the large deviation regime. So this is, somehow studying the particles that are really deviating a lot from the bulk. And this will be where x is of order t. And in this regime, it's been shown in certain cases, which I'll give the references in a minute, but we expect that the fluctuation should be given by a different distribution called the Tracy-Whittem GUE distribution. And well, in particular, this is not Gaussian, right? So this is a very different regime where the fluctuations are no longer Gaussian and are really quite different than the classical setup of independent diffusions. This distribution, the Tracy-Whittem distribution, is something that also originally showed up in random matrix theory. It dictates the fluctuations of the largest eigenvalue of the GUE ensemble. So, yeah. And, because you have these two regimes, the Gaussian and Tracy-Whittem regime, this leads naturally to wondering what happens in between. Is there some crossover in between where you go from Gaussian to Tracy-Whittem, where you go from kind of the typical classical behavior to this non-classical behavior? And it turns out that if you look somehow in this moderate deviation regime where x is of order t to the 3/4, so in between the other two regimes, you see some crossover. And this crossover is given by the KPZ equation. The KPZ equation turns out to be an SPDE that can cross over between the Gaussian and Tracy-Whittem distributions, because it's been shown that if you take certain limits of the KPZ equation, if you take time to infinity, then the distribution of the KPZ equation converges to the Tracy-Whittem distribution. And if you take some limit where time goes to 0, you could recover the Gaussian. So this is an object that can cross over between these two regimes. And it was conjectured that this is precisely what we should see if we look at, x is of order t to the 3/4. And here's a little caricature of these different regimes. And okay, so this is all a conjectural picture, but what is actually known? So the diffusive regime, there are different work studying the Gaussian fluctuation in 2016, which does something analogous for sticky Brownian motion. And there's another work also by Joseph Rosolaga and Sepalainen, again, studying some Gaussian fluctuations for RWRE models. For the large deviation regime, there are only precise results if you look at these exactly solvable cases. So I was mentioning earlier that for the RWRE, if you choose beta weights for your environment, then things are very nice and you could get certain exact formulas. So for that case, they were able to prove Tracy-Whittem fluctuations. It's still open, I guess, to prove that for general weights. And then Barakhan and Rachnovsky proved something analogous, but for sticky Brownian motion, again, only for a certain exactly solvable case of sticky Brownian motion. And up until recently, in the moderate deviation regime, there were a bunch of physics conjectures. So by Le Dussal in theory, they first came up with some physical derivation to predict that you should see the KPZ crossover on order of t to the 3/4. And then Barakhan and Le Dussal were able to compute the moments for the exactly solvable case, so for the beta RWRE, and show that the moments of the quench density converge to the moments of the stochastic heat equation. And very recently, there's work by Haas, Carol Godfrey, Corwin, and Corwin providing numerical evidence also of this crossover. So just to briefly mention this, because it's kind of interesting. So there's Corwin and Corwin. So Ivan Corwin is my advisor, and then Eric Corwin is his brother, and he is a physicist. So Eric is a physicist at the University of Oregon, and they have a physics collaboration with some of their PhD students in Oregon as well, where they're running numerical simulations and also are in the process of doing some physical experiments to actually see this crossover in real models, right? So to actually, the goal is to show that if you have some physical experiment with, maybe some silicon beads and moving through some fluid, you could actually see a crossover where you go from this classical behavior to this Tracy-Whittem fluctuations. And they're working on that. So there's a lot of interesting activity around this on the physics side as well. Might mention more about that soon. So our main result is to prove this conjecture for the RWRE and the moderate deviation regime. So here first is a more informal statement of our result. We have an environment omega. So again, we assume the environment centered with some variance sigma squared. We could take sigma squared to be anything between 0 and 1/4, but excluding 1/4, which was the case of coalescing random walks. And we have this moderate deviation scale. So we're looking at time n times t, and at position n to the 3/4 t plus n to the 1/2 x. And our result says that if we look at the log of the quench density in this scaling, and then add in some correction terms, we're going to converge to the KPZ equation. Somehow what we actually show is using this Kohlhoff solution. So we show that if we look at the quench density and multiply by these correction terms, we converge to the solution of the stochastic heat equation. Now, in particular, we can look at the coefficient that we get, the noise coefficient for the stochastic heat equation is going to be the square root of 8 sigma squared times divided by 1 minus 4 sigma squared. And what's interesting about this coefficient is that it only depends on the second moment of our environment. So this is some type of universality, right? It's like some type of central limit theorem where the limiting equation, it only depends on the second moment of the underlying random environment. And then from the physics perspective, like I was mentioning before, one of the goals of the physics side of things is to measure this coefficient and see what we could learn about some underlying microscopic random environment. So it turns out that this noise coefficient is something that you could attempt to measure for a physical system. And the goal would be to understand what this tells us about the underlying environment. So in this simple example, we see that, maybe we learn about the variance of the underlying environment. There's also some ongoing work that I have with Jacob Haas and Ivan and Eric, where we're trying to generalize to more general random walk type models and try to figure out what the coefficients say more generally for models with longer range jumps. And Shalin also has some work in that direction. So, okay. So what I said before was more of an informal statement of the result. And to make the result rigorous, we need to somehow smooth out the quench density by testing it against some spatial test functions. Just because the noise is so rough, we can't really expect convergence for a fixed x. So this is not going to be so important for the rest of the talk, but just to make things rigorous, we define this field, this random field UN, which is basically just superimposing this quenched probability against these Dirac masses. And then we say that this is tight with respect to topology of continuous functions from 0t to the space of temper distributions. And then any limit point of this coincides with the solution to the stochastic heat equation. Okay, so how do we actually prove that something converges to either the KPZ equation or somehow equivalently the stochastic heat equation? So there are two methods that are commonly used, and they both rely on basically different characterizations of the solution to the stochastic heat equation. So the idea is that somehow we have some characterization for the solution to the stochastic heat equation. We come up with a similar characterization for the thing we're trying to take the limit of, and then hopefully we could take the limit, right, and see that we still have that characterization. So the first method would be to characterize U as a solution to a certain martingale problem. This goes back to work of Bertini and Jackman. And then maybe we could show that the pre-limiting object also satisfies a version of this martingale problem and take limits. Now, the second method that people have used, especially recently, is to write U as a chaos series. I'll get into the definition of that in the next slide. And then basically, if you could show that the pre-limiting model also has the similar series expansion, maybe you could show that using this series representation, your model converges to the stochastic heat equation. Now, this is maybe something unusual, but I want to talk a little bit about the second method, which turns out not to work. So the story of this project is basically the following. There's a paper by Corwin and Gu in 2016 that studied a very similar model to ours. And what they were studying is the RWRE model, but they were in the large deviation regime. So they're in the large deviation regime, but they were also taking a weak noise scaling. So that means as n was going to infinity, they were making the noise weaker and weaker. So this is different than the large deviation regime I mentioned earlier, because that everything I mentioned up until now, we were always fixing the noise. So here they're taking large deviations, but they're also making the noise weaker and weaker. And in that regime, you also expect to get KPZ fluctuations, because somehow you could think that if you have large deviations but make the noise weaker, that's kind of the same as moderate deviations, because yeah, you see the large deviation effect from coming from the noise, but you're making the noise weaker, so it pushes you down back into the moderate deviation regime. So in that setting, they see KPZ fluctuations, and they were able to prove it using this chaos series method. So when we started working on our project, we basically thought we would just try to adopt the same method, and it would be something very quick and simple, and we would get this result, painlessly. So we tried to adopt their method, and we'll see in a minute that it really didn't work. And it was quite puzzling for a while. So let me first explain what this chaos series method is, and then hopefully you'll get kind of a flavor of what's going on in our setting. So basically, the first thing we need is this notion of a mild solution to the stochastic heat equation. So the stochastic heat equation is has to be interpreted, right? Because it doesn't really make sense to take derivatives of white noise type objects. And one way to make sense of the solution to the stochastic heat equation is to give this integrated form. So this is the Duhamel form of the solution to the multiplicative stochastic heat equation. Again, if we assume that Xi was something very smooth, this would just be the Duhamel form of a solution to a deterministic heat equation, right? So basically we're saying that U is equal to the initial data convolved against the heat kernel. And then since we also have this potential U times Xi, we need to keep integrating that out over time. And we have gamma, which is just our noise coefficient. So we say that if U satisfies this equation, it's a mild solution to the stochastic heat equation. But what we could see is that since U appears on both sides, we could just iterate, right? So we could replace U here again with the same expression and keep iterating, and we'll get an infinite series expansion for U. So if we do this, we'll see that U is this has a series expansion, and this is called a chaos series. And the main thing to notice is that the kth term in the series, okay, so we have gamma to the power k, where gamma is the noise coefficient. We have some term which is just product of heat kernels. And then we have an integral against k copies of white noise. So the kth term is a k-fold integral against white noise. And what we want to do is to come up with a similar expansion for our model for the RWRE, and then hope that we could take the limit. So for the RWRE, what plays the role of the white noise? So for us, we have our environment, our omegas, they play the role of the noise in our model. So the natural thing to do is to try to come up with a discrete chaos expansion where instead of a k-fold integral against k copies of white noise, we're going to have sums against products of k omega variables. So we could do this. So we could say PRW is just the transition density of a simple symmetric random walk. So in other words, it's just the probability that at time n, your random walker is at position y. And then since white noise should be centered, we're going to define omega hat to just be a centered version of the omegas, because omega went from 0 to 1. Omega hat will go from -1 to 1. And then somehow it's not so difficult to rearrange this quenched density P omega ny into a series of the following form, where the kth term in the series is going to be a sum against the product of k of the omega hats. So these Z1 to ZK are just going to be possible space-time pairs that you could have along your path from 0, 0 to ny. And you're going to sum over all possible such paths, and you're going to have some coefficient, which is some combinatorial object, counting how many times the points Z1 to ZK could appear in paths from 0, 0 to ny. But anyway, to get into this form is something that's not so difficult to do. And then the idea would be to try to take the limit of this series to something of the form of the chaos series for the stochastic heat equation. So what we can do, well, the first thing we can do is to take a term-by-term limit. So for each term in the discrete chaos series, we could take its limit to a term that looks like a term in the chaos series for the stochastic heat equation. And this is possible to do. So for a fixed term, we could first multiply by all the correct scalings that we had in the moderate deviation regime, and we get convergence to something that looks correct. I mean, this is the type of term we see in the limiting in the chaos series for the stochastic heat equation. The only issue is that the noise coefficient that we get when we do this is 8 sigma squared, or the square root of 8 sigma squared to the k. And we know from the physics conjectures that the actual limiting heat equation should have a larger noise coefficient. It should be the square root of 8 sigma squared over 1 minus 4 sigma squared. So this is where we started to get confused because we weren't getting the right coefficient, which A, we knew didn't match the physics conjecture. And also B, if you think about it a little more, you should see that this can't actually be the correct coefficient of the limiting heat equation because, like I said earlier, the degenerate limit of our model is coalescing random walks, which is the case where sigma squared is equal to 1/4. And we should really expect things to blow up because we can't really expect to get non-trivial fluctuations for the case of coalescing random walks because they're the quenched, there's only one possible path that things could concentrate on, and we don't expect to get our result to hold in that limit. And 8 sigma squared doesn't really blow up at sigma equal to 1/4, whereas the correct coefficient is something that blows up in that limit. So because of this, and I guess because we somehow knew the conjecture, we realized that this method doesn't really work, at least naively trying to take the term-by-term limit of the chaos series cannot yield the correct result, which somehow implies that a failure to commute limits, right? Because we were trying to take a limit of a sum, and somehow this is not turning out to be equal to the sum of the limits of the individual terms. Okay, so this led us to somehow refine our result because we tried to think, okay, well, before this, there's the whole, we actually proved the result using a different method. So I'll get to that in a minute, since this original method did not work. But once we realized, once we had a proof of the result, we realized we should try to understand why the original method wasn't working. And we decided to try to keep track of the environment and see how it converges to the limiting white noise. Because somehow the noise that we were getting in the limit seemed to be larger than the noise that we were starting with for the chaos series approach. So we could define this field C, which is somehow we're just summing up over all these over these environment variables omega hat. So we're just summing them up and rescaling them so that they should converge to a white noise. And this is something, in fact, this does converge to a white noise, but if we keep track of the joint convergence of this field C with the field U, then it turns out that this C doesn't converge to the entire limiting white noise. So this field C converges to C1, which is a space-time white noise, but there's another independent space-time white noise, C2, which also shows up in the limiting stochastic heat equation. So it turns out that U will satisfy a stochastic heat equation where we could break up the white noise into two independent parts. One part has coefficient 8 sigma squared, and the other part has this other coefficient. If you add these two coefficients together, or the sum of the squares, you will get our previous result. So this is just a refinement of the previous result, but it kind of shows that somehow there's more noise that's showing up in the limit. So in the previous method, this was only somehow accounting for part of the noise, and somehow some parts of the chaos series were escaping off, and some of the mass was escaping to infinity, and there's somehow more noise that's appearing in the limit. So because of the failure somehow of the other method, this led us to somehow refine our result in this way. And this is something to explore more. We don't fully understand, I guess, exactly what's going on here, but it seems quite interesting that you have this extra noise appearing in the limit. So, and I guess just to conclude, this is not a definitive answer, but it seems that the thing that's going wrong and the reason the methods of Corwin and Gu don't really work in our setting is because of they were working in this weak noise setting. So it turns out that weak, like having the noise being tuned weakly is somehow very crucial to the chaos series method working in their setting. And since we were fixing the noise, that seems to be what breaks here. So in the end, we need to use the original method, this martingale characterization, martingale problem characterization, and some other martingale techniques to prove our result. So the main tool that we use is certain types of Gersonov transforms and tilting arguments to help us study the quench density. And then we use this martingale problem characterization to characterize the limit. So the martingale problem characterization says the following: if you have some process U, so that if you define this process Y to be U minus this integral of U tested against the second derivative of some test function, if that's a martingale and it has the following quadratic variation, then up to some, you have to maybe impose some growth condition, but U will be unique and will solve the stochastic heat equation. So that's the characterization that we use to characterize our limit as the solution to the stochastic heat equation. Now, I'm not sure, how much more time do I have?
Up to 10 minutes.
10 minutes? Okay. So, okay. So I guess I'll try to do this part. So what I wanted to spend a few minutes on is just discussing these Gersonov methods, because that's somehow the main tool that we really use and the main way that we work with these objects. And as an example, we could see how we use that to prove the convergence of the first two moments. Now, this is not sufficient to prove the full convergence, but it just gives a flavor of the ideas of our proof. So for the first moment computation, I just want to, at the top of the slide, I'm just recalling the definition of U. So this is the random field that we're taking the limit of. And we want to compute its first moment. But we're computing its first moment tested against some spatial test function, because this itself is some random field. We need to test it against the test function. So just unwrapping the definitions, you could just look at the second line, which is basically just, if we test U against a test function, this turns out to be some quenched expectation where we have some horrible prefactor, and then we have just the test function phi acting on our quenched random walk with some drift, because we have this drift coming from the fact that we're in the moderate deviation scale. And now we want to take the expectation of this, where we average out the environment. So when we take the expectation of the right-hand side, we're taking the expectation of the quenched expectation. That's just going to somehow become this annealed expectation, where our random walk will now just become a simple symmetric random walk. Once we average out the environment, the random walk and random environment, a single walker will become a simple symmetric random walk. So this is basically the object that we're studying. It's just the expectation of, we have a simple symmetric random walk, but with some drift, and then we have some prefactor. And the trick that we're going to do is basically to interpret these prefactor as a change of measure that will tilt our random walk to remove the drift. So we have the following fact, which is that for a simple symmetric random walk, this following exponential random variable is a martingale that will act as a change of measure to change the law of a simple symmetric random walk to the law of a new tilted walk, where the probability of jumping to the right is now e to the lambda over 2 cos lambda, and of jumping to the right is e to the minus lambda over the normalization. So we see that, or well, you'll just have to trust me, I guess, because it's on a previous slide, but this coefficient that we had, the CN-TX coefficient, is exactly this change of measure that will tilt our random walk with drift, so that under the new tilted measure, it becomes a centered random walk, or centered up to some small error. And then the idea is that now we just have a centered random walk where we basically have diffusive scaling, because we have nt and we're dividing by square root of n. So in the limit as n goes to infinity, this is just going to converge to the expected value of a Brownian motion, or of the test function acting on a Brownian motion. And that's precisely the first moment of the stochastic heat equation, because if we take the expected value of the stochastic heat equation, we kill the noise term, which has mean 0. We just get a heat equation. So the moments could be, the heat equation, yeah, will give us exactly this expectation over a Brownian motion. So that's the idea for the first moment. And for the second moment, and really all the higher moments, we again will express the expectation of the moment in terms of an expectation over, well, for the second moment, the 2-point motion, we end up getting expectations of the form where we have some of these prefactor terms, and then we just have, phi acting on these random walks, where each random walk has some drift. And the idea is to interpret these prefactors as, again, they're going to be almost martingales up to some terms that we'll have to take into account, but they'll act as martingale changes of measure, and they'll tilt our random walks to become centered. And then we're going to have each of these random walks converge to Brownian motions. And for example, we see here, this is the formula for the second moment of the stochastic heat equation given by Bertini and Cancrini. You have phi of a one Brownian motion and phi of a second independent Brownian motion. And then again, like I said, there's some extra terms we have to insert because we need to take into account the interaction between the walks. So in particular, we get some local time that measures the interaction. That's something we'll have to account for also in the prelimit. But basically, the idea will be to interpret these prefactors as changing the measure. So we go from random walk with drift to centered random walks that converge to these Brownian motions. And then we use these formulas by Bertini, Cancrini, these Feynman-Katz representations of the moments of the stochastic heat equation. Okay, now just for the end, I just want to conclude with one nice application, which also connects back to a more physical motivation. So we've been talking about the quench density, and what would be more physical is to talk about the largest particle. Like what are the fluctuations of the largest particle if you have K particles in your random environment. And we could easily convert our results about the quench density to results about the maximal particle, just using this basic idea, right? If we want to look at the distribution of the largest particle, the probability that it's less than X means all the particles must be less than X. So that's just the kth product of the tail of a single particle, or 1 minus the tail of a single particle being greater or equal to X. And this could be approximated as an exponential. So in this exponent, we have the number of particles, and then we have the tail probability for a single particle. And to use our results, we need to just somehow choose K and T to match the scalings of our results that we had. I guess just a quick note, we didn't study the quench tail, we studied the density. So you replace greater equal to with equal, but by integrating our result for the density, we could get a result for the tail. And then, so there are two ways you could think about this, but if you want, like if you're studying if you have a result about the large deviation behavior, then you can either think of taking a really large number of particles, right? Because if you have one particle, it probably behaves typically. To see large deviation behavior, you need to take a really large number of particles. Or you could think that you have a small number of particles, but you look at a really short time, right? Because for a really small time, maybe the particles are all starting together, so they're sticking together and are having a lot of interaction. As time goes on, they're going to separate and act more and more independently. So if you want to see the large deviation behavior, you either will fix time and take a really large number of particles, or you'll fix the number of particles and take a really short time, right, to see the large deviation. In particular, the large deviation regime will be where time is of order log K, where K is the number of particles, or the other perspective is that K is of order e to the T. So the more physical perspective is to fix the number of particles and look at a short time, just because otherwise the number of particles will grow and be very, be too large to actually work with physically. And it turns out that the moderate deviation regime will be where time is of order log K squared, or alternatively, K, the number of particles, is of order e to the square root of T. And this is exactly the regime where you have a crossover, right? So if you start running your system for a really short time, you're going to have this Tracy-Woodham behavior. If you look at the fluctuation of the largest particle, then you're going to have this crossover when T is of order log K, and then for a very large time, the particles will behave almost independently once they separate and will behave quite classically. So our result, again stated informally, is in the moderate deviation regime, so we take the number of particles to be e to the square root of T. We have our K particles. Then if we look at the maximum particle, and we divide by n to the 1/4, and we'll have to center. There's some deterministic centering terms. Then the fluctuations will be given by the sum of two independent parts. One part is a Gumbel distribution, and the other part will be given by KPZ equation. And what's interesting about this is if you look at the classical setup for independent walkers, the maximal particle, its fluctuations are just given by a Gumbel distribution. So here we could really tease out the two separate effects of the two sources of randomness, right? So we have the randomness from just sampling a bunch of random walks, and that gives us this Gumbel fluctuation. But we also have the randomness from the underlying environment, and that gives us an independent contribution of these KPZ fluctuations. So here, really, you exactly see the two effects. And again, from the physical perspective, you would see that you would try to measure this extra randomness and the fluctuation of the maximal particle for smaller times, right? And you would see that it's larger than you would expect if they were just independent. Okay, so basically, again, you can make this more formal and exactly put in all the scalings, but it's just the same as, yeah, so this is not too important. And then just to conclude, I wanted to say that there's all the results that I presented, we also have analogous results for sticky Brownian motion, but they're really exactly analogous. It's just a continuum version of the model. So sticky Brownian motion is really just a model where you have Brownian motions that act independently when they're apart, but when they touch, they somehow stick together. And by stick together, I just mean that the set of times where they touch has positive measure. It's still going to be a nowhere dense set. So it's not that they actually stick for any interval of time, but it's just that you somehow thicken the set where they're touching, right? Because for regular Brownian motions, they would only touch on a set of measure 0. This is, of course, the definition could be made much more precise, and it turns out this model is really some type of continuum limit of the RWRE, and we have analogous results showing the KPZ fluctuations for this model as well. And again, so what we've shown is that in the moderate deviation regime for these models, we have KPZ fluctuations. So even though the typical particles really behave quite classically, we start seeing in the moderate and large deviation regime the effect of the underlying environment. And then something that was interesting in this model was that the polynomial chaos method failed, and somehow we have independent noise being created in the limit. Also just wanted to point out that our techniques work for any environment, so they don't depend at all on the exactly solvable formulas for the beta case. The results are, or the techniques are quite universal and don't depend on any exact formulas. And then, like I mentioned before, we're trying to work on understanding the noise coefficients for more general models. And then hopefully we're going to tie them into the physical experiments that Parekh is running in his lab. And that's it. So here are the references. Thank you for listening.
Thank you very much, Hindy. Let's see if there are questions or comments from the audience.
Okay. So I was just trying to think about this relation with sticky Brownian motion, right? So in principle, if you look at two particles on the random environment, and then you take something which is very close to Bernoulli, these two particles, they converge to a sticky Brownian motion in the limit, right?
Yeah, exactly. So if you want to get sticky Brownian motion, you first have to diffusively scale the random walks, but you also have to tune the environment to be closer and closer to concentrating at 0 and 1. If you didn't tune the environment, then you would lose all the stickiness in the limit. So exactly, you do have to tune the environment like that. Yeah.
So in that sense, your model is strongly interacting, no? Compared with previous results than in that. So I mean, it's way more. I mean, it is very much expected that the moment method doesn't work because your particles have a stronger interaction between them, no, right? Than in the case of when you do, for example, weak noise limit, no?
Yeah, it could be. I mean, probably that might. Yes, I guess it turns out yes. Maybe we didn't realize right away. Yeah, the sticky Brownian motion case is right. Definitely has a stronger interaction, but yeah, even in the RWRE already, I guess you have that same effect. I guess I just want to point out that the results for sticky Brownian motion are not a limit of the results. Like we prove the results independently. It's not some type, like we can't actually take a limit of the results for RWRE to sticky Brownian motion. So those are done in parallel. But yes, what you're saying, I think that is what's happening, I guess.
Okay. Thank you.
Yeah, thank you.
Let's see if there are more questions or comments. So just one. So what is special about the exactly solvable model? Like, is something about the beta?
Yeah, I guess it's based. I don't have the best answer, but I think there are some formulas for the beta distribution. I mean, I guess.
Okay.
Yeah,
So,
it's about. I mean, the structure of the beta distribution, I guess, gives certain formulas.
So I can think of all these models belonging to the same class, but then the precise formula only for the beta
Yeah.
random walking random environment, okay.
Yeah, I guess it's similar to how like yeah, I mean, for the central limit theorem, right? If you have like coin flips, you have the binomial, you could write out exact formulas. And then, so I guess the beta itself is a pretty large class of distributions, but yeah, I guess they're the nicest ones that take values between 0 and 1.
Mm-hmm. Okay, so let's see if there are no more questions or comment.
So maybe can I ask maybe one more question?
Please.
Sure.
So yeah, so nowadays there's been a kind of a lot of interest in what people call random walks in dynamic random environments, right? So okay, usually they just put one particle on dynamic random environment, but there are a few instances of which they put various independent particles evolving in this dynamic random environment. I don't know if you have seen if you have studied this type of models on which also the idea is usually when they do a dynamic random environment, you put some like for example some particle systems as a random environment, and that gives you both time and space correlations, but at the end of the day there's still some homogenization going on, and then and you still go to the people predict that you will still will still be the picture that you see when you have, like, for example, in your case, a strictly independent time-space environment.
Mm-hmm. Yes. So far, we don't know how to go beyond include time correlation. There's a paper I put a reference to by Shalin. He wrote up some generalization where you could allow, I think, some spatial correlation, but we don't know how to include time correlation. But I think from the physical perspective, probably if you have some nice enough model, the results should be true, but we don't know how to deal with it right now. But yeah, I mean, it's yeah, that's a good question.
Okay, thank you.
Okay, so let's see. I think there are no more questions, so let's thank Hindy. Okay, so we update next Wednesday with another speaker. Okay, bye everyone. Bye Hindy, thanks again.
Bye everyone. Thank you for coming.
Bye Milton.